Now let us talk about Lewis structures. In this section, the learning objective will be drawing of Lewis structures. Generally, we are going to explain how these molecules were drawn in the very beginning. For example, water looks like that. Ammonia would be trigonopyramidal, and so forth and so forth. CO2 is linear. So these are what we call Lewis structures. They include dots to represent electrons, the symbols of elements, and the bonds, knowing that each bond, this is a rule you must know, each bond is made of two electrons that are shared. So two shared electrons. That's what makes each bond. So now let's dig in. A molecular formula only shows the number and identity of all the atoms in a compound, but does not show which atoms are bonded to each other. So what you're saying is this: the molecular formula is the representation of the elements making the chemical or the substance. For example, H2O for water. So the molecular formula for water is H2O. But it does not show which atoms are bound to each other, because a layman will think that this is drawn like this. So wrong. Turns out it's drawn like this. And they're dots, lone pairs on oxygen. So we are going to explain how to arrive here, which is what we call a Lewis structure. The Lewis structure will show the connectivity using bonds between atoms, as well as the location of all bonding and non-bonding valence electrons. Last time we talked about non-bonding valence electrons, and we call them lone pair of electrons. They are lonely because they are not bonded to anything. So that is the idea. Let's do more on this. There are general rules for drawing Lewis structures. Draw only valence electrons, and that means you use valence electrons in bonds and lone pairs. So what this means is that we don't include the core electrons. The next rule is we need to give main group elements except hydrogen an octet of electrons. So hydrogen, for example, in water, can share 2 electrons with oxygen, and he's happy with 2 electrons on him. Okay, so this is kind of the representation of the Lewis dot structure. And I'm going to use blue to show the non-bonded electrons. Now each hydrogen, if you look at each hydrogen here, circling the shared electrons on hydrogen, there are only 2. So hydrogen and helium, they're usually happy with 2. Now if you're looking at or focusing on the oxygen, let me circle it in with this color in the middle. Oxygen here is surrounded by 8 electrons, which is what we call now the octet rule. Okay, and then here comes rule number 3. Each hydrogen has 2 electrons. Oh, I've already explained that, and I'll tell you that most of the time I'll add some rules here. Hydrogens always drawn outside the structure, meaning externally, which is why you see hydrogen and hydrogen out here. You can also see hydrogen on the outside of this structure, methane. Okay, so they're always external. And I can add another one, halogens too. Are usually I say usually because there's a few exceptions where you'll see a halogen right in the middle of the structure, outside the structure. Okay, if you have a structure like this, yes, halogen including chlorine, fluorine, bromine will be outside. If you have a structure like this, yes, halogen, which is the chlorine, 1, 2, 3, 4, is always outside. So I've added a few rules. Maybe I should have called this rule 4 and then I'll call this rule 5. Those are the general rules I follow. Other than another one that other rules that I will show you in the process of drawing Lewis structures. Now let's go on. If you want to draw Lewis structures, there are steps to follow. How to draw a Lewis structure, that's the learning objective on this part. Step number 1, you want to arrange atoms next to each other that you think are bonded to each other, and I'm going to add here, arrange them in symmetry. So what this means is that once you draw your arrangement, try to see if you can cut the molecule into equal half. So for example, if you're given CH4, I would rather draw the atoms, 4 hydrogens and carbon in the middle, knowing that I can cut the molecule. See, the top part is reflected the bottom part, or I can do this, the left side is reflected on the right side. I usually go for symmetry as I arrange them in space. The other thing you can see in CH4 is that the hydrogens, you see them, they are drawn externally, they are drawn outside the structure. I told you hydrogens and halogens like chlorine, fluorine, bromine, iodine will be outside the structure. You don't want to draw it like this. There's no symmetry here. There's no way you can cut that molecule into equal half. And again, there's this rule, hydrogen is inside, and when it's inside, it's gonna need 2 bonds. We described and say that hydrogen should always bond to 1 bond, which is why you don't want this hydrogen in the middle. So this structure is totally wrong. No symmetry, hydrogen in the middle of the structure, not good. So step number 1 is that just arrange the atoms next to each other that you think are bonded to each other, and you arrange them in symmetry. The other thing you want to see here is that carbon is gonna go in the middle for you to get that symmetry, or even carbon can bond more than hydrogen. Hydrogen only bonds once. Carbon can go up to 4. Remember the formula for predicting number of bonds? It was 8 minus the valency of the element. So let's see how many bonds carbon can take. It will be 8 minus, carbon is found in main group 4A, 8 minus 4C. Carbon can take 4 bonds, so why not put it in the middle? That's the motivation of step number 1. Okay, step number 1 also applies in nitrogen. Would you want to draw this structure right here in this form, or would you want to draw it like this? Remember, again, I'm looking for symmetry. So for me, I'm thinking that if I do it this way, the molecule is gonna be happy because it's quite symmetrical. See that? There's a way I can cut it into equal half. I see the same thing up and down. Okay, so now the other thing you can see here is, let me erase this. The other thing I see in this arrangement of my elements is that carbon here, I told you, can take 4 bonds. Nitrogen can take how many bonds? So how many bonds for nitrogen? So it will be 8 minus valency of nitrogen. Nitrogen is found in main group 5A, so predicted valence electrons is 5. So nitrogen can take 3 bonds. So this is a good one. That's a good arrangement, which is just what I have here. because I see nitrogen can take 3 bonds while carbon can take 4 around him. See that? So you are just trying to see how to arrange your elements. You don't want this because here the nitrogen is going to be forced to take nitrogen is going to be forced to take 4 bonds, and when that happens it's going to have a plus charge. Usually we minimize the charges, and here you see there's a problem. Carbon here is denied 4 bonds, so not good. So for the case of CH5N, which is the molecular formula, this is the best arrangement right here. Okay, now let's look at step 2. So once you've arranged your atoms in space, here comes step 2. You want to count the total valence electrons, which will help you to predict the number, which will help you to form those bonds, even predict the number of bonds if you like, and even give you the lone pairs non-bonding electrons. So the rule is for main group elements, the number of valence electrons is equal to the group number. That's true. You saw that I say that carbon found in main group 4A has a valency of 4 electrons. Nitrogen found in the longest, tallest column 5 in the periodic table, 5A, is gonna give you 5 electrons. Okay, hydrogen is in main group 1A, the valency is 1 electron. Okay, so if you are to consider this molecule right here, CH3Cl, I see that I have 1 carbon. Each carbon is has 4 valence electrons because carbon is in 4A. So total 1 times 4 is 4. Then I do have 3 hydrogens. These 3 goes with the hydrogen. There's a 1 here for chlorine, 1 here for carbon. Each hydrogen, like I said, is 1 valent electron because hydrogen is in main group 1A. But I have 3 of them, so 3 times 1 gives me 3. Total from hydrogen, well, this from the 1 carbon, this is from the 3 hydrogens. And then I have 1 chlorine. Chlorine is in main group 7A, which means he brings 7 valence electrons. So you get 7 valent electrons from 1 chlorine. Now you sum them up. That's 7 plus 7. 4 plus 3 is 7. 7 plus 7 gives you 14. 14 valence electrons. These valence electrons is what we are going to use in making bonds, or is what you would use in making bonds and accounting for lone pairs in the structure of CH3Cl. Let us try to draw the structure of CH3Cl. So we are trying to draw the structure of CH3Cl. We're on step number 2. Okay, but I'm going to start from the top. So starting from the top, CH3Cl is probably going to be arranged like this. Remember that, okay, no bond yet. Remember that hydrogens and halogens are always outside, and that gives me some kind of symmetry. I can carry it into equal half. Like if I carry like this, you see the hydrogens are reflected left and right. Okay, so that's step number 1. Step number 2 was to find the sum of valence electrons. So we have 4 valence electrons from the 1 carbon. We do have 3 hydrogens. Each hydrogen brings a valency of 1, so it's 3 times 1. So that gives us 3 valence electrons from the 3 hydrogens, and then we have 1 chlorine. Each chlorine is gonna bring 7 valence electrons because it's in main group 7, so 7. Now if I add all these up, I have a total of 14 valence electrons. Those valence electrons are the ones we're going to use to make bonds. Okay, we'll come back to step number 3. Okay, so you see how it says when drawing Lewis structures, For polyatomic ions, we add 1 electron for each negative, subtract 1 electron for each positive. This is not CH3Cl, does not have any polyatomic ion, so we ignore that. Now we're going to go to step 3. Let's go back to the slides and see. So step 3 says of how to draw a Lewis structure. You need to arrange the electrons around the atom. Place one bond, which means 2 electrons between every 2 atoms. So when I come here, I will draw my spaced out structure, this one, and then I will connect each of those elements using 2 electrons. So I've done that. Let me clean this up. So you can clearly see that we do have 2 dots in between everywhere. So those ones turns out, because they're shared, they give you the covalent bond. Remember, covalent bond is made from sharing electrons between 2 nonmetals. Hydrogen and carbon are nonmetals. So step number 3 is partially done. What else are we told? For main group elements, give no more than 8 electrons. With the exception for hydrogen, that takes no more than 2. Let's see what we've done. Okay, so I see that my carbon here has 8 electrons. My hydrogens, they have 2. Okay, 2 electrons besides them. So that is satisfied. Okay, hydrogen got its 2, and its carbon got its 8. The problem is gonna be the chlorine. Now remember how we've used 8 electrons in here. Those dots, they are 8 electrons. So how many are remaining, given that we have to use 14? So remaining electrons, valence electrons, will be 14 minus the 8 we've used to make the bonds. We are remaining with 6 valence electrons. The 6 valence electrons are going to be added to the chlorine. Let's read the next rule. Use remaining electrons to fill octets with lone pairs, beginning with the atom on the periphery. Periphery just means outside. So which atom is outside? Our chlorine. So the same step 3, since we made our bond already, this chlorine is going to be happy with the extra 6 electrons. And this accounts for all 14 electrons. So the 14 valence electrons accounted for. Okay, so we've accounted for them. And so this means that we are good here. That is the end of this. Otherwise, we would have made multiple bonds. We don't need to. The very last step is always to check for FOMO charges. I don't think we have FOMO charges in here. We are not even given any FOMO charge in there. So this is where I would stop for this one. So the steps I've shown you is exactly what's shown here. We ended here, and you see that the hydrogens are all next to 2 electrons. Remember, one line is 1 bond, is 2 electrons. Chlorine is surrounded by 8, the 2 in the bond and the 6 outside. Remember, we said we called those dots on the outside lone pairs. They are lonely because they are not bonded to in another element, okay? And we've accounted for all the 14 electrons. If you count all those dots, there will be 14. If needed, we would have done multiple bonds, would have drawn multiple bonds, and that would be by sharing. Okay, an example will be the process of getting the Lewis structure of oxygen. Let me show you that. So suppose we need to find the Lewis structure of oxygen, O2. What is the Lewis structure of O2? We're still going to follow our summarized steps that I have here. In this part, that's what we're going to do. So the first thing, you want to draw the elements in space. There's no hydrogen, there's no halogen. So just O and O. symmetry is accounted for because it's linear. For step number 2, we need to count the valence electrons. So we see that we have 2 oxygens. At least I see that I have 2 oxygens. Each oxygen is in main group A, 6A, so to speak. That means each is bringing 6 electrons, so we need to multiply by 2. Total number of valence electrons is gonna be 12 valence electrons. We are not considering the core electrons, only the outermost valence electrons in the electronic configuration of oxygen. Step number 3, we need to arrange the electrons around the atom. So I'm going to draw my 2 oxygens and use 2 electrons to make a bond. Now, out of the 12 valence electrons, I've used 2. I'm left with 10 valence electrons. Those 10 will be evenly given to the oxygens because we remember this oxygen needs an octet. So 1, 2, 3, 4, 5. Those are 10 electrons. There I'll put 2 on one of them. So now I see that this one is surrounded by 8 electrons. He's octet and is very, very happy. Okay. However, if you look closely at this one, you have 4 black dots and 2 red dots shared on that oxygen. This is a 6 electron environment of that oxygen, and he is not happy. He's very, very sad. So the solution to that is going to be looking at the dots. We've used all the 12. Yeah, we've used all the 12 dots electrons. So, but one of the elements is not octet. So because of that, we are going to proceed to step 4. You see how it says here, if all valence electrons are used and an atom still does not have an octet, which is this oxygen's very, very sad, proceed to step 4. What is step 4? Step 4 tells us to use multiple bonds to fill, I'm reading here, step 4, use multiple bonds to fill octets. A double bond contains 4 electrons in 2 electron bonds, and that's what you're going to go for. What we just need to do is sharing. You're going to sharing again to create a double bond. And to do that, we'll go with the one that has an octet already and share using an arrow like that. This is sharing. Sharing creates an extra bond, which is what you are doing. So the two electrons in the lone pair now are shared in between the 2 oxygens. Now remember how we said that every 2 electron is a bond, every 2 electrons shared is a bond. So that there is a double bond. So if I'm to draw the bond now, there will be the black one from the 2 dots, the red one for the 2 dots, and then you still have the non-bonding electrons. Okay, so this will be your final Lewis structure. The formal charges is expected to be 0. Okay, we'll talk about formal charges later if needed. It's expected to be 0. So that's how you get the Lewis structure of oxygen, which will be that, which is what we are looking for. Now, back to the case of multiple bonds in drawing Lewis structures. I've shown you how the double bond can come about. A triple bond is the other case. It contains 6 electrons in 3 2-electron bonds. So what this is telling us here, 3 2-electron bonds, it means that you have 3 pairs of electrons shared. So if you have an element here and you have another element here, in between the element you will have 3 lines. Those 3 lines is what we call triple bonds, because each bond is 2 electrons. So in our case, our element is nitrogen and nitrogen. So let's try and draw the Lewis structure of nitrogen gas, N2G. So let us draw the Lewis structure of nitrogen gas. We're still going to follow the same process. Step number 1, we'll arrange the atoms next to each other, but in a way of symmetry. Again, it's just 2 elements, so it will be linear. Step number 2, we need to find the total valence electrons. Total valence electrons. I have 2 nitrogens. Remember that nitrogen is in main group 5. So he brings 5 electrons. Now you need to add this. It seems like we need to account for 10 valence electrons in the structure of nitrogen gas. Okay, step number 3, it tells me to arrange the electrons around the atom. Place 1 bond, 2 electrons between every 2 atoms. We only have 2 atoms, so I'll give them 2 electrons to share for now. Out of the 10 valence electrons, I'm left with 8 valence electrons. Now, since I want to satisfy octet rule, which means 8 dots surrounding a given element, I have 8 left, so I'm gonna put 4 here and 4 here. Just divide the 8 evenly between the 2 nitrogens. Now there's a problem. If you look closely, if you are to circle what's surrounding this nitrogen, it's 6 electrons. Similarly, if you are to circle what is surrounding the other nitrogen, it's 6 electrons. Both of them are very sad. Why? They are not octet. They are not surrounded by 8, which is why we're going to go to this part of step 3, which reads, if all valence electrons are used up and an atom still does not have an octet, we need to proceed to step 4, where we are going to use multiple bonds to fill up the octet. We want all our elements to have 8 electrons around them. So to do that, what we're going to do, we're going to share 2 electrons at a time. So push this here. It's gonna give you 4 dots now in the middle. Now the left nitrogen only has 1 lone pair left. Now if you look closely, this time around this guy is very happy. He's surrounded by 8 dots, 8 electrons. But the other one, this one, is not happy. He has 6 electrons. The left nitrogen has 6 electrons. He's not happy. So we're going to do it again. So far what we have is this: a double bond and a lone pair on the outside. The nitrogen to the right is happy with 8 electrons, because double bond means 2, 2. 4 bonding electrons, 4 non-bonding electrons. The 4 non-bonding electrons are the 2 lone pairs. So this guy has to share, because the left one shared before. In this step B, the right nitrogen will share. You do that, you're going to get a shared electron lone pair of electrons shared there. You're left with 2 dots on the nitrogen on the right. Those shared electrons are another bond. So this is really the structure of nitrogen gas, the Lewis structure of nitrogen gas. You can tell we've used all our 10 valence electrons, because in the triple bond, those are 6 electrons. Then you have 2 non-bonding, 2 non-bonding. If you add all these up, it's 10 valence electrons. Usually would want to account again for 4 more charges, but there's no need for this one. I'm not gonna go there. So that explains why the structure of nitrogen gas in the slide is written like this, with a triple bond. You need to practice more. So let's look at the case of C2H4. Follow the steps. Step number 1, for me, I would look for symmetry like this. Remember, carbon can take more bonds, so carbon is put in the middle. Okay, carbon is put in the middle because he can bond to more elements. And this is symmetrical because I can do that. You see, I can cut it into equal half. So it's quite symmetrical. Step number 2, we need to count the total valence electrons that will help us to make bonds and lone pair of electrons. Remember, the formula is C2H4. So we do have 2 carbons. Each carbon comes from main group 4A, meaning you have 4 valence electrons each. 2 times 4 is 8. These are from the 2 carbons. Then we do have 4 hydrogens. Each hydrogen comes from main group 1A, so that means the valence electrons is 1. 4 times 1 is 4. Now you want to add these 2 up. The total valence electrons that you'll use to make your bonds and lone pairs, if any, is 12 valence electrons. Okay? Now we use the 12 valence electrons to create bonds or lone pairs. So what I'll do, I'll draw my structure in symmetry, and then I will join using 2 dots. That's the very first thing you want to do, because that's gonna give you now the lines, the first lines that you want to see. Now you can tell that these 2 carbons are not happy. Hydrogens are happy. We said by rule hydrogen is okay with 2 electrons like that. But these carbons right here, they are surrounded by 6 dots. 1, 2, 3, 4, 5, 6. They are not happy. Now if you count the number of electrons we've used in here, 1, 2, 3, 4, 5 pairs, we've used 10 electrons. So how many remaining? 12 minus 10 the electrons. 12 minus 10 electrons will be 2 electrons left. You can put the 2 electrons on one of those carbons. That satisfied that carbon to the right as an octet. 3 bonds is 6 electrons. Each bond is 2 electrons. And then now share. When you share, you are making a bond because 2 electrons drop down here, they make a bond. Each bond is 2 electrons, and that will be the structure. That will be the structure. You share here because this carbon on the left was not an octet, was a sextet. We share, and that will help us to get a double bond. And now if you check, the carbon to the left is happy. He has 4 lines, meaning 8 electrons. The carbon to the right is happy. He has 4 lines, meaning 8 electrons. So the process shown here is that of sharing, again, to give you the double bond. Now each carbon now has an octet. There are exceptions to the octet rule, unfortunately. Of course, I told you hydrogen only takes a maximum of 2 electrons, so does helium. So he only bonds to one other element. Like here, that hydrogen is next to 2 dots. You can tell that the chlorine himself still maintains octet because he has 6 dots. If you want to just follow the process, your Lewis structure would end you here, right here. So hydrogen is an exception, but there are other elements also that don't follow octet rule, and one of them will be boron, and I'll tell you even aluminum and iron also tends to do this. These are the elements in group 3A that are very common. I'm just highlighting boron and aluminum. But like I say, Fe here will also do the same. Elements in group 3A tend not to follow octet rule. They just are fine with 6 electrons. They are fine with an sextet. Okay, so in the case of boron, as shown in this slide, you have BF3. So if someone tells you to write this Lewis structure of BF3, we know the steps. I'm looking for symmetry. Halogens are always outside, just like hydrogens. And then I need to find the total valence electrons. Boron is in main group 3, so 3 electrons. You have 3 fluorines. Each fluorine brings 7 electrons because fluorine is in main group 7. So I have 3 electrons added to 21 electrons. That gives me 24 electrons. So step number 3, I connect my fluorines with 2 dots. That gives me a bond. So that will bring me this far. A bond is 2 electrons. But I see I've only used 6 electrons used out of the 24. Remaining will be 24 minus 6. That's gonna be 18 electrons remaining. So where will the 18 electrons remain? We satisfy the octet rule under step 3. So the fluorines right now only have 2 electrons on them, but we have 18 more electrons to use. I'll give each fluorine 6, and that will account for the 18 extra electrons. So you see, all electrons used up. Someone will say, then make a double bond. If I make a double bond, that will start creating 4 more charges, which Lewis structures don't like. So we would stop here and not force 4 more charge, not force double bonds by sharing to make a double bond on the fluorine, because that will create a 4 more charge plus or minus somewhere in the structure, which we are avoiding if not needed. So the molecule is comfortable with only 6 electrons around the boron. Remember, each bond is 2 electrons. Same thing will happen if you are using aluminum chloride to draw the Lewis structure. Let's say you are doing AlCl3. It will stop here. AlCl3 will also stop there. It's a group 3A element. There are elements that take more than 8, and these are elements in the third row. They have empty d orbitals available that can take more electrons. Okay, these elements include phosphorus and sulfur. They have more than 8 electrons around them when you draw the Lewis structure. For example, if you try drawing the Lewis structure of H3PO4, this is what you'll get, and the phosphorus has 5 bonds. Each bond is 2 electrons, so 10 electrons on phosphorus. Same thing happens for sulfuric acid, H2SO4. The Lewis structure will look like this, with the sulfur there having 6 bonds. So 6 times 2 electrons will give you 12 electrons. This situation is called expanded valence shell. Okay, this situation where elements are taking more than 8 electrons is called expanded valence shell. Those elements have expanded valence shells, and that includes phosphorus and sulfur in this case.